Guys, the test would be on Tuesday of week 7. So in week 7, Tuesday is actually a student-free day. Alright, so that means our test will be bumped to Thursday. And I'll put that on sector already. Okay, so week 7, Monday's a public holiday, Tuesday's student-free day. So then it's just getting bumped back a lesson quarter. Alright, so it still follows that same lesson pattern. So let's jump up here then. We're doing today 3D. And what I want to tell you about both 3D and 3E is we should use our calculator to support us. Okay? But there are some of them, not all of them, but there are some of them that we can work out sort of asymptotes and so forth, roots, just using a mathematical argument. So this one here, this is our function. Part A, find the reciprocal function and state its domain and range. Okay? So the reciprocal function then is going to be 1 on top of x take 1 times x plus 2. Okay, that's what the reciprocal function is. Now, the domain is easy. Okay, it's going to exist for all values except when the denominator is 0. So for the domain, we're going to go x does not equal 1 and x does not equal negative 2. They're the two values that it cannot be. Otherwise, it exists for every other value. Now, for the range, we've got to think about what this function is doing. Firstly, it's a quadratic. Okay, it's a quadratic, so it's got a positive a value, so it's going to open upwards, and its roots are -2 and +1. So I'll just sketch them for you guys, because this is useful for us, because what it means is the minimum. It's a minimum. It occurs halfway between -2 and +1. So the minimum occurs at x is -0.5. So I'm just thinking about those things. That's how I know that. And then you've got that grey table there. Okay, so when we change a function to its rational function, notice how the zeros become the vertical asymptotes. All right, we're going to have vertical asymptotes here. What else do we have? Local max become local minima. Local minima become local max. Okay, so this minimum point is going to become some maximum point. All right, so we're going to use that in a moment. So we know on this function we have a local max at x is -0.5. All right, all okay with that? How I've worked that out? Okay, we can just refer to our calculator, but I'm just giving you some reasoning process behind it. That's from that second dot point here. Okay, so then let's talk about the range, because we're asked to find the domain and the range. The domain was easy. The range is going to be a little bit trickier. Now, one way we can do these things is to just go, well, what happens to the function as x approaches positive infinity? Okay, what happens? Let's investigate. What happens as x approaches positive infinity? So you can just think, right? A good way to think about it is by putting a number in there. If I put 1,000 in here, all right, if I put positive 1,000 where the x is, I'm going to have 1 on 1,000, 1,000 take 1, times 1,000 plus 2. It's 1 on 1,000 times 1,000. Okay? It's 1 on a million. It's a really big number. And as this number gets larger, okay, then it's going to be 1 divided by an even bigger number. Alright, so 1 cake divided by a million people, you get pretty much nothing. In fact, as x approaches infinity, our function, our reciprocal function, I'm just going to call it y, our reciprocal function approaches 0 from the positive side. Okay, it's positive because this is a positive number. Alright? Similarly, let's think about what happens as x approaches negative infinity. So we can think about putting a large negative number in there. So if we put -1,000 here and -1,000 here, right, we've got basically 1 on -1,000 times -1,000. Alright? Which is 1 on positive 1,000,000. So it doesn't matter how far we go to the left, it's still going to be a positive value, and we can see that as x approaches negative infinity, y is still approaching 0 from the positive side. Okay? So if we were to start to sketch this, I might go here start to sketch it. Alright, what we've got so far, we've got a Cartesian plane, we've got an asymptote at x is 1 and x is minus 2. There's a vertical asymptote there, and a vertical asymptote there. Alright. We have a local max at x is minus 0.5. We won't put that on yet because we'll find the y value for that in a moment. But we do know that as x approaches infinity, it approaches 0 from the positive side, and then the same here. As x approaches minus infinity, it approaches 0 from the positive side. So we've sketched a very little bit of the function there. We should also be able to see that as, yeah, I'm trying to think, well, I think we'll see this from the graph, okay, but it's got this feature here. All right, let's talk about the local max then. We have a local max at x is minus 0.5. So that means if I want the y value when x is minus 0.5, I'm going to plug that into here. This is going to be the y value of the reciprocal function. So the y value is going to be 1 on top of minus 0.5 take 1 times minus 0.5 plus 2. Alright, so that's what 1 on minus 1.5 times 1.5. It's minus 1 on 2.25. And it's not very useful like that. Alright, we want to sort of get it as a fraction with a rational denominator. So we'll multiply it by, what do we need to multiply 0.25 of to get a whole number? 4. Alright, so we're going to multiply it by 4 on 4. That's going to be minus 4 on top of 2.25 times 4 is 4 times 2 is 8, and 0.25 times 4 is 1, so that gives us 4 on 9. Okay, so that's the y value of our local max. So if this is our Cartesian plane, minus 4 and 9, it's about there, isn't it? And that's x is half. So that's a local max. That means it's got this thing going on here. Alright, so that's how I've sort of developed a bit of an argument for where different things are happening. Now we haven't answered the range yet. Okay, so we've built up the local max, we've built up that they're approaching 0 from here. So now we can answer the range, right? Because we know that that number there is minus 4 on 9. So for the range, I'm going to just rub that part out so I can put the statement here. We've got y is greater than 0. Alright, so it exists for all values greater than 0. It doesn't exist at 0 because this will never reach 0. It doesn't matter how large you make it, it'll get closer and closer and closer, but it will never get to 0. So that's the first statement. And then the second one is that it has to be less than minus 4 over 9. Less than or equal to, because it passes through that point. It doesn't exist between minus 4 and 9 and 0. It exists above 0 and for values less than or equal to minus 4 and 9. So we have two statements there. All of this information you can get from your graph, right? Use your calculator to support you. Cool, so that is 3D. We'll move on to 3D.